All right, in this video, we are going to talk about the fundamental theorem of calculus. All right, so we have talked about the indefinite integral. That's the set of all antiderivatives of a function. And then we talked about the definite integral. And we talked about how you would go about solving that in general with Riemann sums. And we didn't really talk about the connection between antiderivatives and the Riemann sums. And so, because that's what's called the fundamental theorem of calculus, at least part of it. There's two parts. We're just going to talk about one part in this video. That part of the fundamental theorem of calculus gives a connection between definite integrals, right, which are areas underneath curves or between curves and the x-axis, the net signed area, and antiderivatives. Okay, so it says let f of x be continuous on the closed bounded interval ab, and let cap f be any antiderivative of f of x. Okay, so over here on the left hand side we have the definite integral from a to b of little f. Okay, and so what the fundamental theorem of calculus, at least this part of it, says is if you find any antiderivative, all you've got to do to calculate the area is plug in the upper limit of integration into the antiderivative, and then plug in the lower limit of integration into the antiderivative, and subtract the two. So that's kind of why indefinite integrals have the integral sign as well as the definite integrals, because of the fundamental theorem of calculus. Okay, really on the surface of it, it doesn't seem like there would be much of a connection at all between areas between curves and antiderivatives, but there is, and this is the connection. Okay, so that's a pretty big result. Obviously, if they're going to call it the fundamental theorem of calculus, or if it's part of the fundamental theorem of calculus, it's a big result. Okay. All right, so in the rest of this video, let's just take a really look at a really simple example of how to use this. All right, so here we have a definite integral that we want to evaluate, the integral from minus 1 to 6, 8x cubed plus 2x, okay? And so what we'll do is just find an antiderivative of 8x cubed plus 2x, all right, just one. All right, and so we would go through and integrate that. So looking at the integral of 8x cubed plus 2x, I can see that this is the sum of two functions, right? So by the sum rule, all I need to do is find an antiderivative of 8x cubed and then add an antiderivative of 2x. All right, an antiderivative of 8x cubed, using the constant multiple rule, I would rewrite the constant 8 and then multiply by an antiderivative of x cubed. The antiderivative of, or x cubed and antiderivative of x cubed is 1/4 x to the fourth, and that's using the power rule, right? Add 1 to the power and then divide by the new power, or multiply by 1 over the new power, which is what I did here. Next, the sum rule says put a plus. Then we want to find an antiderivative of 2x, and that's x squared, right? That one's pretty straightforward. All right, so here I have found an antiderivative, right? And this vertical bar basically means to evaluate this antiderivative at these 2 points and then subtract them, okay? So that's a new notation. You may not have seen that before. All right, before you plug in these numbers, so what we're going to do is plug in the 6 into this and plug in the minus 1 and then subtract that. That's essentially what that means. Before you do that, though, I highly encourage you to simplify this. Otherwise, you're creating more work for yourself if you plug in before you simplify. So 8 times a quarter is 2. So now I have the antiderivative completely simplified. Then I am going to plug in the 6 into here. And so that's this part right here. So I plug this top number in, and that's what this bar means, plug in the top number. Then I am going to plug in this bottom number, -1, and that's what you see here. One thing is, if your antiderivative has multiple terms like this one, make sure that you're subtracting off the whole expression. A lot of people will forget to put these parentheses right here and then end up with the wrong answer because they didn't subtract off everything that they needed to subtract it off. Okay. All right, and from there, just start simplifying that out. So 6 to the 4th is 1,296. 6 squared is 36. Negative 1 to the 4th is positive 1 times 2 is 2. Negative 1 squared is positive 1. 2 times 1,296 is 2,592. And plus 36 minus 3, and all of that comes out to be 2,625. Okay, so remember that would be the area of the region bounded by the graph of 8x cubed plus 2x and the x-axis between negative 1 and 6, at least the net signed area, right? The area above the x-axis minus the area below. So you can see we didn't really calculate any of the definite integrals using the definition because it's fairly complicated. This method is much easier. Okay. All right. In the next couple of videos, we'll take a look at a couple more examples.